We will now start to review the individual process steps of a printed circuit board as it travels down the surface mount line. Raw, unpopulated boards are stacked in a device that automatically picks them up and slides them into the stencil printer. The primary function of this machine is to apply solder paste to all the locations on the board that will require a solder joint. A metal stencil is created from board artwork that has openings corresponding to the component pads where solder joints are required. First, the printer moves the board under the stencil. Cameras then locate the small alignment dots called fiducials. These fiducials are etched into the copper artwork on the board and in the stencil. The printer then adjusts the board so that fiducials are accurately aligned under the stencil. It lowers the stencil so that it is in contact with the board. Paste is applied adjacent to a metal blade called a squeegee. The squeegee is then wiped across the stencil, depositing paste in each opening. When the stencil is raised, the paste remains on the board at only the component pad locations. The board is then moved into the next operation. Solder paste has a number of important characteristics, such as viscosity, tackiness, and melting temperature. These characteristics are determined by elements such as the type of flux used, the solder ball size within the paste, and chemical composition of the solder itself. Paste deposit variations can greatly affect finished product yields and reliability by causing short circuits, open circuits, and insufficient unreliable solder joints. Therefore, it is very important to control the process at this machine. Many CMs use statistical process control, SPC, to monitor the machine's operation. The stencils are stored in a rack and removed when a particular board is going to be built. The following daughter card requires a fixture due to its non-rectangular shape. Notice the indentation marks. They are due to the mechanical fixture holding clips. The stencil conforms to the fixture shape. It may impact the stencil life, but is otherwise a usable condition. There is a stencil step-up here at the connector. This is a 7 mil step for the next lev connector. The step-up is visible on the side exposed to the paste. The flat side with no visible step is placed flat against the bare fab. Multi-level stencils are created by etching away material in areas where a thinner stencil is required. For example, this stencil started with a 7 mil foil and was etched away in this whole area except for these two spots. This carrier is used through the entire SMT process. It holds an oddly shaped fab through the assembly process when card edges provide insufficient support for the automated equipment. The tooling holes are in the fixture to align the card. One tooling hole is turned into a slot to compensate for any CTE, coefficient of thermal expansion, mismatch between the fab and fixture as the board transitions through the SMT ovens. This is an open paste printing machine. The tray being loaded is a straight 6, that is, it is 6 mils thick with no steps to alter paste volume. The stencil matches the card you see here on top of the stencil. Notice that the exposed copper areas match the stencil opening locations. The card is fed into the paste machine through the material conveyor and stops directly under the stencil. This non-rectangular daughter card does not require a fixture and instead uses blocks for support during paste. These blocks support the stencil in areas where the fab presents an open space due to an odd shape. As the squeegee traverses the stencil, the blocks support it and prevent deformation and therefore prolong stencil life. This paste machine offers two different non-fixture bottom support methods. It can use magnetic pins, which cling to a metal plate and are positioned to support the back of the board, or it can use blocks. Typically, we use blocks in the first pass because we aren't worried about any bottom side components. However, when the card is flipped over, there are parts to contend with on the back. We then have to use pins, which support the card in those open locations that are free of components. The support pin location fixture is loaded on a metal tray, which is loaded into the machine just like a board, and then the operators drop the pins in through the holes at the proper locations. Squeegee blades are rotated out and cleaned regularly. You can see several squeegees stored here. Another bottom support type is a routed out plate at all component locations. Usually both the top and bottom side plate are present. Although generally used for second pass assembly, the first pass assembly fixture is also used for rework or special conditions. The card being loaded has already gone through bottom side SMT and is now going to have the top side paste printed. Notice the bottom side components, in particular the components close to the board handling edge, must have adequate keep out or they will need to be hand soldered. This can add cost to the assembly. You can see the bottom support plate here with the stencil located directly above it. Paste is added to the front of the stencil. For process traceability, each tube of solder is scanned and associated with the serial numbers of the boards. Paste composition is sometimes changed to increase paste release, to decrease solder voiding during the SMT reflow, or to decrease slumping of the paste. Slumping is an effect that generates solder beads when paste doesn't remain on the solder pad. As mentioned earlier, changing the flux, solder bead size, or the chemical makeup of the solder can change these aspects and produce the desired results for a particular application. The board serial number is scanned before it is loaded into the paste machine. This is an assembly fixture for a very small card. The labeling requirement of small cards makes stenciling difficult due to the label height. This often results in stencil etching on the board side to relieve areas where the label will lift the stencil. The clamps were specially made for this card. It's a bit more elaborate than the standard fixture, but like others, it remains with the card for the duration of the SMT process. The clamps that hold the board down are machined to give way and provide a constant pressure to the PCBA. These clamps will also allow the card to expand and contract as it goes through the heating and cooling of the oven. The AOI, Automated Optical Inspection, provides input to the statistical process control. The AOI display shows each location being inspected on the left, while the zoomed-out image on the right highlights the area of the board being inspected. This graphic shows several common stencil printer machines used by our CMs and their associated specifications. This slide provides more detail on the design of stencils. They are typically made of a sheet of stainless steel approximately 5 mils thick. Openings where the paste is to be deposited are typically laser cut using the paste artwork Gerber layer. The paste layer is created during the PCB design process. The CM selects the stencil thickness to provide more or less paste volume. The CM may also adjust the stencil openings to optimize the soldering process and subsequent yields. For example, the CM may want to reduce paste volume on the pads of quad flat pack packages, QFPs, to reduce solder bridges. Paste deposition is optimized through an iterative process based on experiences and vendor recommendations.